This lecture is a continuation of my earlier lectures on basic quantum mechanics. Today I will discuss the quantum harmonic oscillator problem. Before addressing the quantum oscillator problem, let us recap the classical harmonic oscillator first. The Hamiltonian of a classical harmonic oscillator, we can write down the Hamiltonian. The Hamiltonian is equal to p square by 2m plus v of x, where this is the kinetic energy part, this is potential energy, and we are considering the problem here in one dimension, and the explicit form of this potential for this classical harmonic oscillator, we can write it explicitly, the Hamiltonian, in this way. This is half m omega square x square, and if we plot the potential Vx against x, that will actually look like this. This will be a parabola. This looks like this. So this is my potential energy for the oscillator. Physically, we can imagine a simple harmonic motion of an oscillator like that. A simple pendulum. We can actually imagine a simple pendulum which is having this simple harmonic motion. So like that. So it is having this simple harmonic motion. The potential Vx looks like this. This is a parabola. So I have shown here the potential energy term, which is this function. So I show this potential energy over here. Usually we do not have a perfect simple harmonic oscillator or the oscillator potential like this, but in many practical situations the potential is approximately parabolic in the neighborhood of a local minimum. The actual potential may be of this form in many realistic situations. The potential is not exactly parabolic, but the potential can be of this form, where I'm plotting a general potential function. So this is my x axis, this is the potential, so which can be something like this, Now we can see that here in this region we can see that the potential looks like a parabola. So the actual potential may be of this form, which has a minimum at this point. So here the potential has a minimum, so I say this point as x0. So at x0 this potential has a minimum. Formally, if we expand this potential function Vx in a Taylor series about this minimum, the mathematical form of this function Vx will be, we can write it as Vx is equal to V of x0 plus V prime x0 x minus x0 plus half V double prime x naught x minus x naught whole square, and then there will be the higher order terms. In this expansion will be there, and here this V prime is the derivative. Actually V prime x is the derivative of this function Vx, and V double prime is the second derivative. V double prime is the second derivative of this function, d square V by dx square. Now we can see from this expansion that V of x naught is this minimum point. So this is a constant. And this first derivative of the function at this point, minimum point x0, the derivative should be 0 because x0 is the minimum point of the function. So this term will vanish. So V prime at x naught, that is equal to 0, because x0 is the extremum point or the minimum point of the function. So first derivative should vanish, and then we have, this will be V of x naught plus half V double prime x naught, that is second derivative of the function at that point, and the higher powers of x minus x naught, and the higher order derivatives will be there in the Taylor expansion. So here we can see that the function V at x naught, this is a constant, so it actually gives you a constant shift of the energy. V of x naught is a constant, and so this will actually contribute to a constant value to the potential. So we can set that as my 0 level, then this term I will not consider or neglect, and the potential becomes half V double prime x naught x minus x naught square, and I am neglecting actually here the higher order terms in the expansion. So the potential becomes this. So V of x is now approximated to this thing, half V double prime x naught x minus x naught whole square. So this function now looks like a parabola around this point. So it is it looks like almost a parabola here around this minimum point, so it is approximately a parabola here. So now I can choose this point x naught, so I will choose x naught to be 0 and the second derivative at this point x naught. So this v double prime at x naught, I can, this number, this will be a constant, I can fix it to be m omega square, then this becomes half m omega square x square. So in this way this potential becomes approximately a parabolic function, and this looks like that potential of a harmonic oscillator. So this represents then approximately a potential for a harmonic oscillator around this minimum point. I set it to be 0 here. So this is the potential now. So this is the Hamiltonian for a classical harmonic oscillator, and we can write down the Hamilton's equations of motion. So the Hamilton's equations of motions are x dot is equal to del h by del p, and the second equation is p dot is equal to minus del h by del x. So this Hamiltonian is a function of x and p. So x dot means dx by dt, the time derivative of x, so that will be del h by del p, the partial derivative of the Hamiltonian with respect to the momentum. So what is that? So if you do the derivative with respect to momentum here, so what we obtain, that will be 1 by 2m, and the derivative of this function p square will give me twice p. So this 2 and 2 cancels, so we have p by m. So x dot, this x dot means dx by dt, so dx by dt becomes p by m here, and from this equation the time derivative of the momentum dp by dt, that is equal to partial derivative of the Hamiltonian with respect to x. So from here we have minus half m omega square, that is constant, and the derivative of x square with respect to x is twice x. So these 2 and 2 cancel, so we have minus m omega square x, minus m omega square x. So this is the time derivative of the momentum. Now what we will do, we will take the time derivative of this equation one more time. So if I take the time derivative of this equation, take the derivative on both sides. So from this equation we have d dt of dx by dt, that is d square x by dt square, and on the right hand side we have 1 by m dp by dt. On the right hand side 1 by m time derivative of p, so that will be dp by dt. Now we will use this Hamilton's equation over here, because we have dp by dt is equal to minus m omega square x. So that equation, this second equation, we will use it here. So from this we will obtain then 1 by m dp by dt. So what is dp by dt? dp by dt is equal to minus m omega square x. So let me substitute this over here, minus m omega square x, then this m cancels. So what we have finally is minus omega square x. So this becomes minus omega square x. So this is the second derivative of the position. So d square x by dt square, ultimately we are having this equation, d square x by dt square is equal to minus omega square x. So we all know about this equation for a simple harmonic oscillator. We all know about this equation for a simple harmonic oscillator, and we know the solution of this second order differential equation, which I will write next. So using these classical Hamilton's equations of motion for this harmonic oscillator, what we have until now is this equation. So we got this equation actually, the second derivative of x, d square x by dt square is equal to minus omega square x. A general solution of this second order linear differential equation can be of this form. So I am writing the expression of this solution for this second order differential equation, which can be written in this way: a constant a cosine omega t plus another constant b sine omega t. Because it is a second order differential equation, so we have two undetermined constants a and b, so which we have to determine the constant values of the constants a and b can be determined by the use of initial conditions. So here we will apply the initial condition at t equal to 0. So first initial condition is that at my initial time t is equal to 0, the value of the function x is x naught. So if we substitute this condition over here, what we get from this x naught will be equal to cosine 0 is 1 and sine 0 is 0. So this term will vanish and we will only have a here. So the constant a is determined in terms of the initial value of x0. So I can write down the solution as x of t is equal to a is my x0 now, x0 cosine omega t plus b sine omega t. So here we notice that one constant is determined, now another constant b is still there, so which we will determine in next using another initial condition. So until now what we have is x of t is equal to x naught cosine omega t plus b sine omega t. Now what I will do, I will take a derivative of this function. So I will take dx by dt, that is x dot t, which is dx by dt, the time derivative of this function. So time derivative of cosine is, the time derivative of this cosine function will be minus omega sine omega t. So minus omega x naught is there, sine omega t plus the time derivative of this function sine omega t is omega cosine omega t. So b omega cosine omega t. So this is the time derivative of the function x dot, and from the Hamilton's equation, we know that x dot t is equal to pt by m, that is p by m. So I can equate x dot to p by m. So I am using that Hamilton's equation over here. So p by m, the time derivative of the position x, that is x dot is equal to p by m. So p by m is my this thing on the right hand side. So I am writing it here, minus omega x naught sine omega t plus b omega cosine omega t. This is what we have until now. Now what we will do, we will apply another initial condition, that at t is equal to 0, that is at the initial time the value of the momentum pt is equal to p of 0. This is the initial momentum for the particle having this harmonic motion. So once we substitute this, from here we can see what we have is p0 by m on the left hand side, and on the right hand side we put t equal to 0, then this term will vanish because sine 0 is 0 and cosine 0 is 1. So here b omega. So from this equation we have determined the value of the constant b, right? So the value of the constant b is, we have from here p0 by m omega, So we have the value of the constant b also. Now we will substitute the value of this constant over here. So then we have the final solution for x. So we are substituting this value of this constant over here to get the solution. So then this will be equal to x naught cosine omega t plus what is b, p0 by m omega sine omega t. So we have now the solution of x at any given time. What is the value of x? So if we know the initial position and initial momentum for the particle, we can determine the final position from this equation. And to obtain the solution for the momentum, this is the solution for position x, and to obtain the solution for momentum we will use again this equation. So we obtain the solution for x here, and to get the solution for p, that is momentum, we again use this equation of Hamilton's equation, x dot is equal to p by m. So we remember that we have just used that equation and we had the expression x dot is equal to p by m, if you remember, and the expression was this, minus x naught omega sine omega t plus b omega cosine omega t. So from here we have this p, it is a function of time, that is equal to m times this thing. So we just cross multiplication, we are doing this cross multiplication. So this becomes minus m omega x naught sine omega t plus m times this term, and we know the value of the constant b. The value of the constant b is already determined, so we substitute that p0 by m omega. So we already know the value of b, and this is multiplied by m, so there should be m here, and then omega cosine omega t. So this cancels with that. So finally we have minus m omega x naught sine omega t plus p0 cosine omega t. So this is the solution for p, and actually we can easily get that from here also. If you just do the time derivative of x, we will get the same equation, because time derivative of x we can directly calculate from here, will give us this solution. So now we have solution for both x and p. So now we clearly write down the solution, whatever we have now obtained. Over here we just write it down. So finally we have the solution for x and p for this classical harmonic oscillator as x of t is equal to x0 cosine omega t plus p0 by m omega sine omega t, and the solution for momentum, the momentum at any particular time t will be equal to, which we already obtained the expression, minus m omega x naught sine omega t plus p naught cosine omega t. So these are the solutions for a classical harmonic oscillator, the position and momentum expression at any given time t. Next we go to the quantum harmonic oscillator. So we have seen how the position and momentum of a classical harmonic oscillator evolves with time. We have derived that using the Hamilton's equation of motion. Now we are going to the quantum version of this problem. So basically quantum harmonic oscillator. Now for this quantum harmonic oscillator also, the Hamiltonian has the same form, but here the difference is that the Hamiltonian is now an operator. In quantum mechanics, we know that corresponding to the physical observables, we have operators associated to each physical observable. So for Hamiltonian, there is an operator h hat. So I am putting a hat here to indicate that these are now operators. These are not just a normal function. Yeah, similarly the momentum is also an operator and position is also an operator in quantum mechanics. So this is the quantum Hamiltonian for the harmonic oscillator problem, and x and p, these are now operators. These are now operators, position and momentum operator, and they satisfy this commutation relation. So bracket x comma p, this commutation relation satisfied by these operators IH bar and an identity operator. So these are operators and they satisfy this commutation relation. So what is the meaning of this commutation? xp minus px. Now this is the problem. So why this quantum harmonic oscillator problem is so important? Because quantum harmonic oscillator problem is important in the context of recent quantum technology also. So to understand various quantum systems, for example nanomechanical and hybrid optomechanical systems, superconducting electrical circuits with Josephson junctions, that is various superconducting qubits and resonators, quantized electromagnetic field. So the electromagnetic field, we know that it can be expressed in terms of electric field and magnetic field, and then the Hamiltonian there exactly looks like a harmonic oscillator, and we can quantize it. So quantized electromagnetic field, atom photon interactions and quantum optics in general. Qubit oscillator system, circuit QED, continuous variable system, very important system now for quantum information and quantum computation, continuous variable quantum systems, and many more systems are there where this quantum harmonic oscillator problem is relevant. So for quantum case, now this position and momentum, they are Hermitian operators, so that's why we put hat here. And we will also now evaluate the time dynamics of these operators, and in the Heisenberg picture these operators x and p evolves with time according to these equations. So in the Heisenberg picture, the operator x evolves according to this equation, time derivative of this operator xt is equal to 1 by I h bar, where h bar is just h by 2 pi, Planck's constant divided by 2 pi, x comma h, where this bracket x comma h is the commutator between the position operator and this Hamiltonian operator, and the momentum operator evolves according to this equation. I am again writing the Heisenberg equation for momentum operator. D dt, time derivative of the momentum operator, is equal to 1 by I h bar p t comma h. So where x, this operator xt and pt, they are now the operator in the Heisenberg picture, and we know that in Heisenberg picture operator evolves with time and the quantum state doesn't evolve. We will come to that. Now as I said that these operator x and t, they are the operators in the Heisenberg picture. So in the Heisenberg picture, these operator observables x and p evolve with time. So this operator I am writing it explicitly, that Heisenberg picture operators x, xt, what is that? That is e to the power I h t by h bar x e to the power minus I h t over h bar and pt, and in the Heisenberg picture this momentum operator pt is similarly e to the power I h t by h bar p e to the power minus I h t by h bar. So these are the now the time evolution for this position and momentum operators in quantum mechanics. So earlier we have solved the problem for the classical harmonic oscillator using Hamilton's equation of motion. Now we are using the Heisenberg equation. Here these are called Heisenberg's equation of equations of motion, and these are the Heisenberg picture operators. So that means position and momentum operators in the Heisenberg picture. So now let us try to solve this Heisenberg equation. Derivative, time derivative of x operator is equal to 1 by I h bar, the operator commutation between the x and h, commutator between the operator xt and the Hamiltonian. We can simplify this expression on the right hand side. So let us substitute the explicit form of this Heisenberg operator x. So what is that? We already know that this x hat t, that is this we already know that this Heisenberg picture operator xt is actually e to the power I h t by h bar x e to the power minus I h t by h bar. So this is the Heisenberg picture operator x of t. Now what is the if I break this commutator, it will have two terms actually, x h minus h x. So I have written x t over here, then I have h minus h, and then again the Heisenberg picture operator, this one. So I am writing it here, e to the power I h t by h bar x e to the power minus I h t by h bar. So I have actually explicitly written down the commutator. I break it into two terms like that. So better to put the bracket, a different bracket, so that to distinguish that from this commutator. So this is a normal bracket here. So I am putting a normal bracket, and now we can see from here that this operator e to the power minus I h t by h bar and this Hamiltonian operator, they commute with each other, so that I can bring it in front of that. I means e to the power this operator times this will be equal to h times this operator. So I can exchange the position of this Hamiltonian, because these and these two operators commute with each other. So similarly here also these two operator h and e to the power I h t, because if we expand this exponential operator, it will have 1 plus I h t by h bar plus 1 by factorial 2 this whole square blah blah blah. So that those in the expansion h will commute with all the term in the expansion. So these two operator, as a result these two operator will commute. So I can actually exchange their position. So that's what I am going to do, 1 by I h bar. So I can bring it here. Yes, I can. So I can bring this h here, e to the power I h bar x, then I write h here, and then the operator e to the power minus IHT by H bar, and here also I put H here, and this I shift the position between these two operators. So I first write, because they commute, that's why I can do it. Otherwise, normally in quantum mechanics, generally any two operators, they may not commute with each other, and so this I write first and then H, and then whatever we have I am writing e to the power minus I HT by H bar. So now we have written it in a very nice form. So now we can see that this operator and this operator, and so we can see that in the middle there is this operator XH, and these unitary operators act from left and right. So here also there is this operator, and the unitary operators are acting from left and right. So from the linearity of this operation, I can write it down as 1 by H bar, IH bar, e to the power IHT by H bar, and then I am writing XH minus Hx e to the power minus IHT by H bar, because if you break this term, this unitary operators will linearly act on this, and effectively then we will get these two terms. So I can write this thing in this way. Now we can see that this is just the commutator between the operator X and H. So I will write it down here. So this will be 1 by IH bar e to the power IHT by H bar. This is my commutator between X and H, and this operator is there, this unitary operator e to the power minus IHT by H bar. So this way I have simplified this Heisenberg equation here. So next what we will do, we will calculate the commutator x comma h, and then finally we will have the Heisenberg equation of motion for the position operator in a nice form. So these are the operator here. So if there is no, so everywhere these h, x, p, all these operators are not normal function, they are now quantum mechanical operators. So until now what we have is the time derivative of this position operator is 1 by IH bar, and we have simplified this term in this way, e to the power IHT by H bar x comma h commutator, and then minus e to the power minus IHT by H bar. So it is clear that now we need to calculate the commutator between the position operator and the Hamiltonian. So Hamiltonian is this. So let us now evaluate the this commutator x comma h, x comma h, and then we will substitute that over here. So x comma h commutator is this commutator. So this x comma h, this commutator is equal to, okay, we have to calculate the commutator between the position and the Hamiltonian. So here if you see that, so I explicitly, it is better to write explicitly, x comma p square by 2m, p square by 2m plus half m omega square x square. So this is my commutator I have to evaluate. Now it is clear that x will commute with x, right? So in the commutator that part will not contribute. So what we have is x comma p square by 2m. So I can write it in this way, this 1 by 2m I can bring it outside, and that will be just x comma p square, and that will be 1 by 2m x comma p square means p times p. Now we know that the commutator between now we know this commutation rule actually. So we know this commutator in quantum mechanics, if there is an operator A and there is an operator B and C. So it is B times C. So I am calculating the commutator between A and BC. So that commutator is equal to A comma B, this commutator multiplied by C plus B A comma C. So I will use this commutation relation for this one. So what will be that? So that will be 1 by 2m is there outside, and this commutator I will follow this x comma p. So we will treat this as A, this as B, and this as C, and then the commutator is x comma p. This commutation multiplied by the operator C plus B. B means here P operator P, and then the commutator of A and C means X and P. So I close the bracket here. So now we know that the commutator between the position and momentum operator X and P is IH bar times the identity. So I will not explicitly write the identity everywhere. It is implicit that the identity operator is there for this commutator, because when operators P will be multiplied with this operator, this identity operator, that will give me P again. But X comma P, okay, so let us substitute that over here. So this will be 1 by 2m X comma P. This commutator is IH bar, identity operator, identity multiplied by P will give me P. This is P first term plus second term P, and what is X comma P? Again IH bar identity. So P multiplied by the identity operator will give me P, and there is IH bar, the constant factor is there. So we have to write that, and we close the bracket over here. Then finally we have 1 by 2m. This is IH bar P. This is also IH bar P. So this is twice IH bar P operator. So this is equal to, this 2 will cancel with this one. So this is IH bar by M, the momentum operator. So we will use this result, the commutator between the position operator and the Hamiltonian. Finally it becomes IH bar by MP. So I will substitute that result over here. So I will substitute that result over here to get the time evolution of the position operator. From this Heisenberg equation we will have the equation of motion. So this is equal to, so this is finally equal to 1 by IH bar e to the power, this unitary operator, e to the power I H T by H bar. And what is the value of this commutator? The value of this commutator we have already evaluated, that is IH bar by M P. And then this unitary operator e to the power minus IHT, that operator is still there, this one. So here we can notice that this IH bar cancels with this IH bar. So this IH bar cancels with this one. So finally we will have 1 by M. E to the power IHT by H bar, the momentum operator, and then this unitary operator again. So this means unitary operator again. Now we can see that this is exactly the momentum operator in the Heisenberg picture, right? So we will substitute that. So this is equal to 1 by M, the momentum operator in the Heisenberg picture, P of T. This e to the power IHT by H bar, P e to the power minus IHT by H bar. This is exactly the momentum operator in the Heisenberg picture. So essentially now we have got the Heisenberg equation of motion for the position operator. So we will write it down, and then next we will see how the time derivative of momentum operator evolves. I mean, we will see that how the Heisenberg equation for the momentum operator looks like. So we will do that next. So until now what we have got, we have obtained a nice form for this Heisenberg equation of motion for the position operator. ddt of xt is equal to 1 by p hat t. Here all these operator x hat and p hat, they are in the Heisenberg picture. They are Heisenberg picture operators. Now similarly we can have a nice form of the Heisenberg equation of motion for the momentum operator also. So we already know that the Heisenberg equation for the momentum operator, time derivative of the momentum operator is equal to 1 by IH bar P pt comma H, and here I will write it in a useful form so that we can use the commutator, and so the similar thing what we did for the position operator case. So this can be written as 1 by IH bar, and this is a commutator P comma H. The meaning of this commutator is PTH minus HPT, and PT is the Heisenberg picture operator. So I will write it explicitly for PT. What is PT? PT is this Heisenberg picture operator e to the power IHT by H bar P e to the power minus IHT by H bar. So this is my PT. Then I have to write H, and PT is again the Heisenberg picture operator. So I have to write it here explicitly, I h t by h bar p e to the power minus I h t by h bar. And again we will argue the same thing, that h commutes with this operator, so I can bring it here, and here also I can bring this h over here because these two operator h and e to the power I h t by h bar, they commute, and using that we can finally get this expression. So we can write this as 1 by I bar e to the power I t h t by h bar, and then we will have ph in the middle, ph minus hp, so that thing we will have, and then this operator e to the power minus iht by h bar. So I am doing the same thing what we did for the position operator time evolution. Now this is again the commutator between p and h, so I will write it. So these unitaries, they actually act linearly, so these two operator will first act on this and then on this to have these two terms, so that we will have these two terms. So before that I have not explicitly written that step where I have actually flipped the position of h over here and the position of h over there, then we will get this expression. And so now this is the commutator between the momentum p and h, so I will write it here, 1 by I h bar e to the power I h t by h bar p comma the commutator between these operators p comma h, this one, and then this unitary operator is still there, so e to the power minus I h t by h bar. So now we have to find out the expression for this commutator p comma h. We have the Hamiltonian over here, so we will calculate this commutator p comma h here. So until now we have the time evolution for the momentum operator. We have written this Heisenberg equation of motion in this nice form, and if we can evaluate this commutator, then we will have a nice form of this differential equation like that what we obtained over there for position operator in the Heisenberg equation of motion for the position operator. So our aim is to find out a similar equation for the momentum operator. To get that, now we have to evaluate this commutator p comma h. The Hamiltonian is there, so what is p comma h? Let us evaluate. P comma h, that is equal to p comma p square by 2m plus half m omega square x square. The commutator between the momentum operator and the Hamiltonian operator is this. So this will be equal to, now we can see that momentum operator will commute with this p square because they are moment, this is p times p, and they will commute. Now we will only, the term which will only contribute in the commutator is p comma this thing. So this will be equal to p comma half m omega square x square, this commutator, and now this constant factor I can bring it outside, so I can write it as half m omega square, then p comma x square, p comma x square. So I can write it in this way, half m omega square p comma x into x. X square is just x multiplied by these two operator multiplication, x into x. So then again we will use that commutation relation for three operator a comma b times c, which is a comma b c plus b a comma c. So we will use this commutation relation for these three operator. So it treat a, this as a, this b and c. So then I can write it down in this way, half m omega square p comma x, p comma so there is a bracket, there will be a bracket, so p comma x, that means a comma b, then c, plus b means x here, and then p comma x, p comma x. Now we know that the commutator between x and p, that is x comma p, this commutator is just I h bar identity. So we will use that, and what will be p comma x? P comma x will be just minus of this thing, p comma x will be just, this will be minus I h bar this. So we will use this relation over there. So that will be equal to 1 by 2 m omega square, p comma x is minus I h bar and identity, and then there is x operator. So this is x, and here also x, and then this commutator is just minus I h bar, minus I h bar identity, and multiplied by x means the operator x again. So this is minus I h bar x minus I h bar x, so that is minus twice I h bar x. So finally what we will have is that 2 factor will be cancelled, and then we will obtain just minus I h bar m omega square x. So this is the value of this commutator p comma h. So this commutator, this relation, this result we will use over here. So we will substitute the value of this p comma h as minus I h bar m omega square x over here to get the nice form of the Heisenberg equation of motion, to get the nice form of the Heisenberg equation of motion. So we will do that. So finally we substitute this commutator which we have already evaluated, this p comma h, that is minus I h bar m omega square x. So we substitute over here 1 by I h bar e to the power I h t by h bar, then this commutator p comma h, that means this one, minus I h bar m omega square x operator, and then e to the power minus I h t by h bar. So this constant factor is there, so I can actually bring it out, and here we can notice that this I h bar and I h bar, they cancel. So we will effectively will have minus m omega square, then this unitary I h t by h bar, and there is this position operator x e to the power minus I h t by h bar. Now we can see that this is my Heisenberg picture operator of the position. So I will write it here, minus m omega square, and this is the so by the way I should mention here that this, when I am writing just x without this t, that means these are Schrodinger picture operator, and this whole thing is the Heisenberg picture operator x of t. And we know that the Heisenberg picture operator, if we put t equal to 0 here, then that will actually give me the Schrodinger picture operator x. So that is the difference between the Schrodinger picture x and this Heisenberg picture x. So now we are working in the Heisenberg picture, and we are dealing with this position and momentum operator and their time evolution. And now, so everything what we are actually calculating, those this position, momentum, they are in the Heisenberg picture. We have to keep it in our mind, and so this becomes the time derivative of the momentum operator becomes equal to minus m omega square x of t, x hat t. So we had earlier obtained this equation for the position operator. This is the Heisenberg picture, this is the Heisenberg equation of motion for position operator, where both of them are in the Heisenberg picture here, x t p t, and here also we have the Heisenberg equation of motion for the momentum operator, which is the time derivative of this Heisenberg picture momentum operator is equal to minus m omega square x t. So we now write down these two equations, and then we will see what is the solution for this operator x t and p t. So finally, until now we have obtained the Heisenberg equation of motions for the position and momentum operator. The time derivative of x t we got in this form 1 by m p t, and the time derivative of the momentum operator, time derivative of the momentum operator is equal to minus m omega square x hat t. So these operator x and p, they are Heisenberg picture operator, and they satisfy these two coupled differential equations. But now they are not just function, they are actually here this x hat and p hat, they are operators. So now we have the Heisenberg equation of motion for the position and momentum operator, and the exact time evolution of these operators we will see how they look like. So for quantum harmonic oscillator, now we have the Heisenberg equation of motion for this Heisenberg picture operator x hat and p hat. So we have these two equations for this quantum harmonic oscillator, and we remember that for classical harmonic oscillator case also we got similar equation, and we obtained that using the classical Hamilton's equation of motion. So please remember that for classical harmonic oscillator also we got similar equation, exactly similar equation for the position and momentum, where we used, for the classical case we used the Hamilton's equation of motion. So for classical harmonic oscillator, for classical harmonic oscillator also we got exactly similar equations for the position and momentum. So d dt of xt was equal to d dt of xt. Time derivative of position was just p by m, p by pt by m, and the time derivative of the momentum was minus m omega square xt. But here this x and p, they are like continuous variable. They could take any value, a real value actually. So position can take any value between minus infinity to plus infinity. For the classical case, this is position and momentum, they are continuous variable here, and here in the quantum case the difference is that this x hat and p hat, they are now operators. Usually they have a matrix representation when we express these operators in some basis. So they are basically, we can imagine them as an operator or the matrix, but they satisfy these x and p, these operators also satisfy similar differential equation, and we expect a similar solution. So basically here in the case of classical harmonic oscillator, we remember that in the classical case we took a second derivative of this equation. In classical case we consider the second derivative, taking the time derivative of this equation. Again we got this another equation, d square x by dt square. So in the left hand side, and on the right hand side we had 1 by m, time derivative of this thing dp by dt, and dp by dt we use the second Hamilton's equation of motion, because dp by dt is this one. So we got finally 1 by m and minus m omega square x, minus m omega square xt, and this m cancels with this, so we got minus omega square xt. And the solution of this equation, we considered a general solution of this equation as xt. This is a second order differential equation on x. A general solution of this equation is in this form: a cosine omega t plus b sine omega t. So we will do the same thing here. Now this is a differential equation, and so we will take the time derivative of this equation as we did for the classical harmonic oscillator case. So if you take the time derivative of this equation, we will get d square by dt square x hat is equal to 1 by m ddt of pt. Now time derivative of pt, from this second Heisenberg equation we can substitute this ddt of pt is equal to this one. So we have 1 by m, and in place of this we can substitute minus m omega square xt, and this cancels. So then we ultimately have this omega square xt. So you see here also the position operator satisfies same type of equation as we had for the classical case. The only difference is that now the differential equation we are considering is for operators, and the solution for this differential equation will also have a general form like this. So we can write a general solution for this equation as x hat t is equal to a cosine omega t plus b sine omega t, because both satisfy this x hat and the x normal position. They satisfy a similar differential equation, second order linear differential equation. The general solution will have also the similar structure, but the only difference here will be that a and b here they are constants, here they will be operators. So here a and b, they are operators. That is the only difference, and we will start with this solution and then we will get the similar solution for x and t. We will see that. So finally we got the Heisenberg equation of motion for the position and momentum operators. I am writing it again so that all the steps we can follow. So this was my Heisenberg equation of motion for the position and momentum operators. Ddt of pt is equal to minus minus m omega square x t, and if we take the time derivative of this equation, we had obtained this equation, d square dt square x hat equal to minus omega square x hat t, where we have used the second after taking the time derivative of this equation, we used the second Heisenberg equation, and then finally we got this equation, and we argued that the general solution of this equation will have the, because this differential equation has the same structure what we got for the classical harmonic oscillator, so the general solution of this equation, the operator equation, will also have a similar or the same structure of solution. So a general solution for this equation is of the same form that we have taken for the normal differential equation for this position and momentum variables in the case of classical harmonic oscillator. So now the only difference is that these are operators, so the solution will be like this. A is now operator instead of constant, so this A cosine omega t plus B hat sine omega t. Now A, I am repeating it again, that now here A and B are operators instead of just a number. So we can now apply the initial condition again here. So let us say that at the initial time t is equal to 0, my operator xt is equal to x0. Basically this x hat 0 is the position operator in the Schrodinger picture, and this is in the Heisenberg picture. So that is basically, if you go from if you want to see that operator in the Schrodinger picture and Heisenberg, that is exactly the case. Using this initial condition, at t equal to 0 means this term will vanish, and this will be 1, and this will be x0. So this initial condition will give us x hat 0 is equal to A hat. So we will substitute x0 in place of A, we will substitute this one here. So xt becomes x0 cosine omega t plus we still have another unknown operator B sine omega t, and what we will do the same thing what we did for the classical case. We will take the time derivative of this x here again, time derivative of x from this equation. If we take the time derivative, that will be ddt of xt is 1 by m pt. I will use that also, that Heisenberg equation also, so I am writing it here. So that is, and I am taking the time derivative on the right hand side. So what we will get, we will obtain time derivative of this will give us minus omega sine omega t. So that means x hat 0 and then minus omega sine omega t, and then next term will be b hat omega cosine omega t. So then we have that we will get PTA right from here. So I will do this cross multiplication. So I will multiply this expression by this m to get the expression for p here. So let us write it down. So from here we have pt is equal to minus m omega sine minus m omega x hat 0 sine omega t and m omega plus this b is there, m omega cosine omega t. So from this equation we will use another initial condition, that at t equal to 0 pt will be my p0. So that initial condition we will apply here. So now we will apply the second initial condition, that at t equal to 0, at t is equal to 0, this momentum operator pt is equal to p0. That means the Heisenberg picture operator becomes the Schrodinger picture operator p0. So this initial condition we will apply it here. So then at t equal to 0, this term will vanish and this will be 1. So what we will have from here, p at t equal to 0, this will be p0 will be equal to, so p0 will be equal to minus m omega x0. So from here what we will have here, if I put t equal to 0, this will be p0 and this will be 0, and from here we will have just b m omega. So p0 is b hat m omega. So then we will have the operator b, so we can determine the value, this operator b hat is equal to p hat 0 by m omega. So now we know both a hat and b hat. So the solution for x is determined. So the solution for x, let me write it here. The solution for x xt will be a cosine omega t. Now a is determined by the initial condition, so this is x naught cosine omega t, cosine omega t plus b hat is also determined here, p hat 0 by m omega, and then sine omega t. So sine omega t. So this is the solution for this Heisenberg picture operator, and we can also get the solution for p. So the solution for p from here we can obtain that, right? So p hat t is equal to minus m omega x hat 0 sine omega t plus capital B hat this. Now B hat is already determined, so I will just substitute it here. So P hat t will be minus m omega x0 sine omega t plus b m omega cos omega t. So what is b? B is already determined by this initial condition. So then let me write it down. Plus b is p0 by m omega and m omega cosine omega t, m omega cosine omega t. Actually this m omega and m omega will cancel. So the solution will be like p hat t is equal to p0 cosine omega t. So p hat t will be p0 cosine omega t minus m omega x0 sine omega t. Now we have to only remember that we are dealing with this position and momentum operators, and this x0 and p0, they are the initial time operator. That means x0 is basically x hat at t equal to 0 and p0 is equal to p hat at time t equal to 0, and we know that from this these are Heisenberg picture operator, and if we put t equal to 0 then we actually go to the Schrodinger picture operators x0 and p0. So x0 and p0, these are the position and momentum operator in the Schrodinger picture. So let me write down the solution for this position and momentum operator separately, what we got, and then we will compare the quantum case and the classical case side by side. What are the similarity? The similarity is in the solution. The structure of the solutions are the same, but we have to remember that in the case of quantum harmonic oscillator, in the case of quantum, we are dealing with the position and momentum operators, whereas in the case of classical harmonic oscillator, we are dealing with continuous variables, position and momentum x and p. And in the case of in the quantum case, these operators x hat and p hat, they can be represented by some matrix. They can be represented by matrices when we write down the operators in some basis, in energy basis or any other basis. So we when we write down these operators in some basis, they will basically be matrices, and in the next step we will actually see the comparison between the classical and quantum harmonic oscillator side by side. So we will write down the solutions and the physical implication of the solutions in the case of classical harmonic oscillator and in the case of quantum harmonic oscillator. We will see in quantum case these operators are not enough. We need the states also. So that we will talk about in the and then in the next lecture we will also talk about the states. But before going that, let us have a side by side comparison between the classical harmonic oscillator and quantum harmonic oscillators. Let us summarize the results that we have for the classical and quantum harmonic oscillators, and we try to understand the qualitative difference between the classical and quantum results side by side. So first we consider the classical case. So first we discuss the case of classical harmonic oscillator, where we have the Hamiltonian for the classical harmonic oscillator was p square by 2m plus the kinetic energy plus the potential m omega square half m omega square x square, and using the Hamilton's equation of motion we obtained the time evolution of position and momentum. So the time evolution of the position and momentums were this xt was x0, we already have it, right? So cosine omega t plus p0 divided by m omega sine omega t, and pt we already have the expression of pt is equal to p0 cosine omega t minus m omega x0 sin omega t, where x0 and p0 are the initial position and momentum. So once you fix that, the position and momentum at any given time is determined from this Hamilton's equation of motion, or the trajectories we also say. So once we fix this initial position and initial momentum for this classical harmonic oscillator, the position and the momentum at any given time t is determined by these two equations. And in fact, the solutions, this xt and pt at any given time, these solutions, they actually represent a point in the phase space. So in the phase space, we can draw it here somewhere. So if we draw the phase space for this classical harmonic oscillator, so this is my x axis and this is the momentum axis, then we will have a these trajectories will represent an ellipse actually. So something like this. So the phase space trajectory for the classical harmonic oscillator will be represented by this. And as I said, that once we fix the initial position and the momentum, the energy of the oscillator is also fixed, because from here, once this initial position and momentum is fixed, the position and momentum at any given time is also fixed actually. At any given time, what will be the position and momentum, that will also be fixed, because so the most important thing is this one. So once we fix the initial position and initial momentum for this classical harmonic oscillator, the energy of the oscillator is also fixed. So we can say that for a particular x0 and p0, x0 and for a particular fixed initial position and initial momentum, the energy is fixed, because once this fixed, these are also fixed, and this Hamiltonian will be conserved. That means energy is conserved. This is a conserved system. So this is the equation for the energy, and from here this equation can also be expressed or written. So this equation I can write it down. So what is this? P square by 2m plus half m omega square x square is equal to E. The energy is fixed, so I can express this equation as x square by something like this, 2E by m omega square root of this thing whole square, plus p square divided by square root of 2me whole square. This is equal to 1. So actually I have rewritten the same equation in this form, and we can easily see that this is the equation for an ellipse, because we know that the equation for an ellipse is something like this: x square by a square plus y square by b square is equal to 1. So this energy equation actually gives us an ellipse, and that represents the phase space. So that equation actually represents an ellipse, and any point on that ellipse is given by this xt and pt. So any point here actually is represented by this xt and pt. That is a point in the phase space for this harmonic oscillator. And from this equation we can see that if we fix from this equation, we can easily see that if we fix initial position and momentum for this, as a particular case, if someone fix this initial position to be 0 and initial momentum also to be 0, then the energy, then what will happen if we fix the initial position and initial momentum both to be 0, then we can see that the oscillator can have 0 energy. So the oscillator will have a minimum energy, so that minimum energy is 0. The energy of the oscillator will be 0. So this means you can imagine of a pendulum which is oscillating, performing this harmonic oscillator, but if the pendulum is at rest, then this condition will be satisfied, that the initial position and initial momentum both are 0, then the energy of the oscillator is also 0. So this is possible in for the classical oscillator. We will see that for the quantum case, actually we cannot set both the position and momentum to be 0. So we will discuss next the quantum harmonic oscillator and some qualitative difference between the classical and quantum oscillator. Next we see the case of a quantum harmonic oscillator. So next we discuss the quantum case for this problem. So we have already seen that the Hamiltonian is now an operator for this quantum harmonic oscillator, which is equal to p square by twice m plus half m omega square x square. So only difference is there. Now this Hamiltonian position, momentum, they are operators. That's why I put a hat here in this quantum case. And using the Heisenberg equation of motion, we already obtained the time evolution of this position and momentum operators as follows. So the position operator at any given time is equal to x hat 0 cosine omega t plus p hat 0 by m omega sine omega t, and the momentum operator at any given time pt is equal to p hat 0 cosine omega t minus m omega x hat 0 sine omega t. So here, although we know the exact dynamics of the position and momentum operators xt and pt, we cannot assign any value to these operators before we make a measurement. So this is a very important difference between the classical and quantum. This is a very important point in quantum mechanics, that we cannot assign any value prior to measurement. We cannot assign any value to these operators as we could for the classical harmonic oscillator. We could fix x0 and p0 to some values, but before doing any measurement, we cannot assign any values to these operators before we make a measurement. And the measurement results will be in this quantum case. In this quantum case, the measurement results will be given by the eigenvalues of these operators xt and pt. So the main a very important, a crucial difference between from classical is here. Now these are operators, and although we know the exact dynamics of the position and momentum operators xt and pt, we cannot assign any value to these operators before we make a measurement. And the measurement results, and when we do the measurement outcomes or the measurement results are given by the eigenvalues of these operators xt and pt. This is the prescription in the quantum mechanics, and from the quantum prescription, measurement outcomes will occur in probabilistic way. That means we will have to repeatedly do the measurements, and in one case we will get one particular eigenvalue, and in the second case we can have another eigenvalue of this operator. So in that way, the measurement outcomes will occur in a probabilistic fashion in general, if it is not in the eigenstate. So now we make a very important statement, that although we predict the dynamics of the operators deterministically, we cannot predict the measurement outcomes deterministically in the case of quantum harmonic oscillator. So those measurement outcomes will occur in a statistical or probabilistic way. And quantum mechanics actually gives us what quantum mechanics actually provide us, the quantum predictions or quantum mechanical predictions. Hence the quantum predictions are fundamentally probabilistic. And quantum mechanics provides the statistical predictions of these observables xt, pt, or the Hamiltonian observable, whatever we want to measure. The quantum mechanics actually gives us a statistical prediction. So that is a very important difference between the classical harmonic oscillator and for the quantum oscillator. To pinpoint the difference between classical and quantum, here I should actually make a statement about the quantum prediction. So the quantum, according to quantum prescription, so here we are considering in the Heisenberg picture, quantum mechanics in the Heisenberg picture. So according to the quantum prescription, according to quantum prescription in the Heisenberg picture, we have actually this time evolution. We have used the Heisenberg picture operators and Heisenberg's equation of motion to determine the position and momentum operator at any given time. Now what quantum prescription actually tells us, that these observables are not enough. We need to know about the quantum state as well. So we need to know about the quantum state at initial time, because in the Heisenberg picture these observables evolve with time, but the quantum state psi does not evolve. So that's why I have given a 0 here. So this is my initial state, and in the Heisenberg picture, once I provide the initial state, the state remains that time evolution occurs for the operators or the observables, and in this picture the state remains this state will not have a time evolution. And according to this Heisenberg picture, once we provide the initial state, once we provide this state, quantum state psi 0, Kate I have written in the Dirac notation, and once we have the state of the quantum system, or here for the quantum harmonic oscillator, we can predict the measurement statistics of various observables. For example, we can calculate the average position, average momentum, or the fluctuations of these operators also. For example, this one we can, once we have the initial state or the quantum state in this Heisenberg picture, we will have all the necessary statistics for the system. So for example, we can calculate the average position. So this is my state and this is the operator. So this will give me the average position at any given time, and we can have the average momentum also. So this is mathematically we write it as this average position. Similarly, we can have the average momentum. Average momentum is equal to psi bra psi, then the momentum operator, and Kate psi 0. We can predict about the average momentum also. Also we can predict about this type of fluctuations, x square average psi 0, or we can have a fluctuation in the momentum, something like this, bra psi 0 pt p square t psi 0. So once we have the initial state and in the Heisenberg picture, the time evolution of the observables we can have from the Heisenberg equation of motion. So this is the Heisenberg equation of motion for an observable, and for position O becomes x and momentum O becomes p. For any observable we can have the time evolution of the operator from this Heisenberg equation of motion, and once we provide the initial state or the state of the system, we can estimate the expectation values for those operators, and this is the thing which quantum mechanics actually gives us, that prediction about the statistical predictions. Several statistical predictions we obtain from this quantum mechanics. So quantum mechanics here specifically in the Heisenberg picture we are discussing. Heisenberg picture, Heisenberg picture. In the Heisenberg picture, this is the prescription of quantum mechanics. Now in my next lecture I will discuss about the energy eigenstates and energy eigenvalues of the quantum harmonic oscillator, where we will see a sharp contrast between classical and quantum harmonic oscillators. We will see that quantum harmonic oscillators have discrete energy levels or discrete energy eigenvalues and energy eigenstates, that we will see in the next lecture. And another sharp contrast in quantum mechanics or the quantum harmonic oscillator case is that we cannot precisely determine both the position and momentum of the oscillating particle due to Heisenberg's uncertainty principle or uncertainty relation, and this is why we do not have the phase space trajectory for the quantum harmonic oscillator case. So here we cannot show you a phase space in the phase space diagram, or we cannot draw a phase space diagram. That means for this quantum harmonic oscillator case we will not have a phase space trajectory. So unlike in the case of classical harmonic oscillator, where we showed that this oscillator can have both the position and momentum, we can have a precise values of the position and the momentum for classical oscillators, but for quantum oscillator we cannot have this we cannot precisely determine both the position and momentum of the oscillating particle due to the Heisenberg's uncertainty relation. So that is a very big difference between the classical and quantum. Yeah, I briefly mentioned about another interesting point here, the difference between the classical and quantum harmonic oscillator. In the case of classical harmonic oscillators, we could fix the initial values for the position and momentum in this way, right? We have seen that we could fix the position and momentum in this way. For this case, the energy for which the oscillator will have minimum energy, the energy will be 0. But for the quantum harmonic oscillator case, this is classical, we could fix both the position and momentum to be 0, then the energy is 0, because according to the energy equation, we can see that the energy will be 0 here, but for the quantum harmonic oscillator case, we cannot set both this x and p to be 0. This is not possible. We cannot precisely determine both the position and momentum at any given time t equal to 0. Say for example at t equal to 0, we cannot have the value for this position operator and the momentum operator at the same time. So we cannot set both of them to be 0 at t equal to 0. We cannot precisely, this is because we cannot precisely determine both the position and momentum at a given time. So this is not possible in quantum case. So, and even if we consider the quantum oscillator to be in the ground state, so if we consider the quantum oscillator in the ground state, the minimum energy state, even in that case there will be a minimum 0 point energy. In that case also we will see that there will be a minimum 0 point energy of this value, and for this quantum case we can say at most when the oscillator is in the ground state, what we can actually say, we can say at most that the average position of the oscillator, that is 0. The average momentum also, the average momentum for the oscillator when it is in the ground state, that is also 0. So the average values, both the average can have the value 0. So we can say at most that the average values of the position and momentum to be 0, but there will be fluctuations, namely these things will have a non-vanishing value. For example, this type of fluctuations will be there, x square. So this will be non-zero, this will have a value h bar divided by 2 m omega. Similarly, the fluctuations in the momentum also, this will be non-zero, p square. If we calculate the expectation value of this operator, p square 0, then for this ground state we will see that it will have a value of h bar m omega by 2. Then we can estimate this quantity delta x. Delta x is called the uncertainty in position. So the uncertainty will be square root of x square average minus x average square, and from here if we substitute the values, then delta x will be square root of h bar by twice m omega, and the uncertainty in momentum delta p will be square root of p square average minus p average square. That will have a value for the system when the system or the quantum oscillator is in the ground state. The value of delta p will be p square average minus p average square. So we substitute those values here. So that will give you square root of h bar m omega by 2, square root of h bar m omega by 2, and then if we multiply delta x and delta p, if we multiply these values delta x and delta p, that will give you a value of h bar by 2. So we see that even their mean values are 0, they will have a small fluctuations, and because of that the ground state energy is also non-vanishing, and also due to this uncertainty in the position and momentum, this Heisenberg uncertainty principle is also satisfied. The Heisenberg uncertainty principle is delta x delta p greater than equal to h bar by 2. So this is the equation for this quantum oscillator in the ground state. So this is the minimum uncertainty, but in general the Heisenberg uncertainty principle says that delta x delta p should be greater than equal to h bar by 2. So this is the minimum uncertainty for the ground state harmonic oscillator, and for higher excited state actually we will have this multiplied by n plus half whole square, something like that. So if the oscillator is in the higher excited state, then you will have uncertainty more than h bar by 2. So that is precisely the Heisenberg uncertainty principle. So for quantum case, the Heisenberg uncertainty principle is satisfied. Thanks for watching. Please don't forget to subscribe the channel and tap the bell icon to get notified for my new lecture videos. Please comment below. Your thoughts and suggestions would be greatly appreciated.